Welcome to Lab 3 about circuits. So, in terms of introduction, the purpose of this laboratory is to be able to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. So, for the background, some important concepts are the principles of energy conservation, which states that total energy and charge in the system will remain constant. And within this, you can determine the node rule and the loop rule, which is that the current in should be equal to the current out, and the sum of all electric potential differences should equal to zero. You also should consider current conservation and charge conservation, along with the definition of steady state, and then also time dependence in RC circuits. So for this experiment, we'll be using an online ideal circuit in which the resistance of wires, ammeters, and batteries are assumed to be negligible. And the setup is that the system is the circuit and then surroundings are everything that is not the circuit. And sources of error can be human error associated with not stopping the watch exactly on time during this experiment. So for the first part of this, the prediction was that I1 will equal to I2 due to the node rule, and the circuit contained two 1.5 voltage batteries, two emitters, one 47 ohm resistor, and one 100 ohm resistor. And the resistance was found by adding those two resistances, so 47 plus 100 equals 147 ohms, and then I was found by dividing V by R, so 3 divided by 147, which was equal to 0.02 amperes, and that was also found to be the actual value. And the current was found to be the same, even though the connections were reversed here. And so for this part, we have the voltmeter, which is 3 volts, and the current, which is 0 amperes. And so the potential differences were found just from subtracting the certain letters by one another of those volts, and you can see the values all there. And then delta V was also found to be 0, which we know through the loop rule, and there was no change in the voltmeter because of the high level of resistance, which would reduce the flow. And here is the round trip potential plot in which you can see delta V always going back to 0 at the end. And so in this part of the experiment, the ammeter is parallel with the resistor, with the current being 0.06 amperes. And the ammeter has a low resistance, which means that more current will go through the ammeter than the 100 ohm resistor. And the overall resistance is decreased, and the current will increase as a result. And here you can also see the calculations for resistance being V divided by I to get all those ohm values, which are all there for different parts of the circuit. And we saw here slightly higher values due to the precision of the ammeter in the model being slightly smaller. And then here we have an RC circuit with two bulbs, one being 10 ohms, one being 20 ohms, one battery of 9 volts, one capacitor with a value of 200 microfarads. Yeah, 200. And then for the battery and the 10 ohm bulb and the capacitor, the light brightens and dims, and the current decreases from max to 0, and the capacitor charges to the maximum. And then for the charged capacitor and the 10 ohm bulb, the light also brightens and dims, the current decreases from max to 0, but the charge on the capacitor decreases as it's discharging. And the times for the capacitor to charge and discharge are listed below, for the 10 ohms being 10.3 and 15.1 seconds, and for 20 ohms being 15.8 and 17.4 seconds. And then here's the data plotted for the RC circuit with the 9V battery, 200 mF capacitor, and 30 ohm bulb. So using the equation ln of delta V divided by delta V naught is equal to negative T divided by RC, we can kind of plot that line of best fit and that slope to get the time. So in the experiment, the time was approximately 6.2 seconds, and using the slope of the data, it was also found to be 6.2 seconds. And then with the actual time being 6 seconds, the calculated time, multiplying 30 ohms by 200 mF was also equal to 6 seconds. And in terms of addressing the additional questions, the first question was, what if you were doing this experiment in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So a real ammeter does not have zero resistance, which would mean that some current would go into the resistor, which would contribute to a lower current overall. And the second question is, what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So in an ideal model, the capacitor would charge immediately, but in real life, this is not possible. This is due to the resistance in the wires and the batteries with internal resistance. Thank you.